Welcome. In this new video we are going to deal with the force on a current carrying conductor in a magnetic field. The force on a current carrying conductor. Force on a current carrying conductor. The force on a current carrying conductor in a magnetic field. In a magnetic field. We have discussed about the magnetic effect of electric current in the previous video. Means when electric current passes through a conductor like the copper wire or any other conductor, it creates a magnetic field around it. If the magnetic field is present in the vicinity of this current carrying conductor, and if another magnet is brought near this current carrying conductor, this the magnetic field created by the electric current carrying conductor must interact with the magnetic field of other magnets brought near the conductor. We know that, see here, this is a setup, means electric circuit, in which a wire is stretched along the length of a aluminum rod, and it is tied with the wire through the rods of the stand clamp. This is a permanent magnet, horseshoe magnet or U-shaped magnet, in which the two poles north and south are near each other. They form a uniform magnetic field between the north and south pole. We know that magnetic lines of force arise from north pole and terminates at the south pole. If we bring the two poles of magnet close to each other, the magnetic field lines become parallel and uniform between the two poles. That is why horseshoe magnet is taken for this demonstration. I have just told you that electric current passing through a conductor creates a magnetic field. If it has a magnetic field, it must exert force on some other magnetic field, because we know that action and reaction must take place simultaneously. So if the magnetic field of the current carrying conductor exerts a force on some other magnet, then the magnet must exert equal and opposite force on the current carrying conductor as per the Newton's third law of motion. Means to every action there is equal and opposite reaction. So if the magnetic field of the current carrying conductor exerts a force on the other magnet present in its vicinity, then the magnet brought near the current carrying conductor must exert the equal amount of force in opposite direction on the current carrying conductor. This was experimentally verified by Ampere. By performing a simple experiment, the setup of this simple experiment is like this. An aluminum rod is tied with the insulated copper wire, and the length of this current carrying conductor is stretched along the length of the aluminum wire, and it is suspended with the stand clamp or the rods of the stand clamp. Now this aluminum rod is suspended in such a way that the rod remains suspended between the north and south pole of the U-shaped magnet, like this. Suppose that this is the north pole and this is the south pole of the horseshoe magnet, and imagine that this is the aluminum rod. This aluminum rod is made to tied with the copper wire, thick copper wire along its length, and with the two ends of this wire it is suspended through the magnetic suspended through the rod of the stand, in such a way that suppose this is the north and south pole of a U-shaped magnet, and this aluminum rod along with the copper wire stretched along its length is suspended with the help of the stand clamp, and the two ends of this wire is connected to the two ends of the battery, that is negative and positive terminals of the battery, and the circuit is completed by using the key plug and ammeter, so that we can measure the current with the help of ammeter. Let the direction of electric current in this way, that is from positive terminals to the negative terminal. Now suppose electric current is passing through this rod. So as soon as the setup is completed and circuit is made, then in order to have the effect of magnetic field on the current carrying conductor, this setup is used here. So initially the magnetic field lines are directed along north pole to the south pole, north pole to the south pole of this magnet, and the aluminum rod is suspended at right angles to the direction of this uniform magnetic field between north and south pole. Now as soon as key is inserted to the plug fitted in the circuit, we observe that deflection in the aluminum rod. Deflection in the aluminum rod. If we take out the key from the plug, the aluminum rod comes back to its original position. Further inserting the key, it experiences the same deflection. We observe the same deflection. Suppose that the deflection is along this direction, means along the left side. If we change the direction of current in the circuit, then after inserting the key into the plug, in this time we observe that the deflection is opposite to the previous state, previous deflection. Means if current is passing from left to right, the deflection is opposite to the direction when right to left. Means after changing the direction of electric current in the conductor, the direction of deflection is also reversed. Not only the change in direction of electric current, if we change the position of magnetic field, means direction of magnetic field by changing the position of the poles of the U-shaped magnet. Suppose that here initially north pole is kept below and south pole is kept up. If we reverse the direction of this field by inverting the poles, like if north pole is here and south pole is here, then if the direction is in upward direction at first condition, then this will be in opposite condition, opposite direction in this changed magnetic field. So either we change the direction of electric current or the direction of magnetic field, the deflection in the aluminum rod gets reversed or changed. Now, from this observation, we have observed that there is a force acting at right angles to each other. One is the magnetic force field due to the permanent magnet, that is U-shaped magnet, and the another, the magnetic field developed due to the current carrying conductor. These two forces act each other at right angles to this. So when these two forces are at right angles to this, then the deflection in the magnetic field is observed at right angle to these two forces. Suppose the force due to magnetic field of the permanent magnet and the force due to the magnetic field of the current carrying conductor are coplanar. Then the deflection in the aluminum rod is observed at right angles to these two forces. It is well be defined or expressed in terms of a rule known as Fleming's left hand rule. Fleming's left hand rule. So Fleming's left hand rule is a rule which provides the direction of deflection in the current carrying conductor when it is allowed to suspend in a magnetic field at right angles to each other. Fleming's left hand rule may be understood like this. The rule states that if we stretch the thumb, forefinger and the middle finger. Forefinger is also known as index finger. So in some of the text you may have the term forefinger. And this middle finger, forefinger is also known as first finger, the middle finger is known as second finger, and this is thumb. So any name is coined here, it doesn't matter. See here, these three fingers, these three means forefinger, middle finger and the thumb. Forefinger means forefinger, middle finger and the thumb. If we stretch all the three at right angles to each other, such that magnetic field lines due to the permanent magnet is supposed to be along the forefinger. Means forefinger points towards the direction of magnetic field. The middle finger points towards the direction of electric current passing through the conductor. Then the thumb will point towards the deflection in the current carrying conductor. That is, suppose that in this way I have stretched the three fingers, then middle finger represents the direction of electric current, forefinger represents the direction of magnetic field. Then what will be the direction of deflection of this current carrying conductor? That is, it will be along the direction of direction of thumb. That is, as soon as current is passed through the circuit, the current carrying conductor will deflect in the direction of thumb. That is, if it was initially in this position, then the current carrying conductor will be deflected in upward direction. Means if it was initially like this, then after passing the current, the conductor, this middle finger means this may be considered as the current carrying conductor, which is here mounted on the aluminum rod along its length. Then the deflection will be observed in the aluminum rod in the direction of this thumb. That is, after passing the current, the aluminum rod will be deflected in upward direction. That is, along the direction of thumb. Suppose direction of current is reversed. What will happen? See here. If direction of current is reversed, suppose that this is along this direction. If we change the direction like this, what will happen? This is the direction of thumb. If the direction of thumb was initially upward, then now the direction of thumb will be in the downward direction. Means this is the direction of magnetic field, and now it is the direction of electric current passing through the conductor, which is mounted on the aluminum rod. So this is the aluminum rod. This is the direction of magnetic field, that is from north to south. Then the aluminum rod, that is, this is aluminum rod, it will be deflected in the downward direction now. So this is how we can express the direction, we can find out the direction of deflection of deflection of the current carrying conductor in the magnetic field. This is known as Fleming's left hand rule. So anywhere we can apply this. If we want to know the deflection in the deflection in the current carrying conductor when it is placed in a magnetic field generated by external magnet. This external magnet may be a permanent magnet or the electromagnet. Just we have already discussed about the electromagnet. when the current carrying coil is mounted over the soft iron core or rod, the iron rod behaves like an electromagnet. So, electromagnet may be used here. That is, if the U-shaped magnet is replaced by the electromagnet, it behaves like an electromagnet. So, this is the simple way of representing the deflection in the current carrying conductor when it is placed in the magnetic field. What is the use of this effect? We will use this magnetic effect or effect of the force generated due to the electromagnet and the permanent magnet on the current carrying conductor, by which a mechanical movement is observed by the use of these two electromagnets, means electromagnetic fields. Due to the two electromagnetic fields, due to the two magnetic fields lying at right angles to each other, that is perpendicular to each other, may generate mechanical motion or movement in the current carrying conductor, which will be the direction of which will be obtained by using the Fleming's left hand rule. The most use of this effect is observed or utilized to generate, to construct the motor. The principle of electric motor is based on this effect of magnetic field on the current carrying conductor that is observed as a mechanical movement. So, in motor, what we observe? Motor is a device, electrical device, in which electrical energy is converted into mechanical energy using the magnetic field inside the motor, either by permanent magnet or by electromagnet, whatever be the case. But in common practices, we observe the mechanical movement due to the electromagnet, because electromagnet can be controlled by our desire. Permanent magnet cannot be removed, magnetism cannot be removed. So, as per our requirement, we can create the magnetic field by the presence of electric current, or it may be removed. So, the effect of this experimentation is used to generate or create the mechanical motion by the motor, which will be, the principle of motor will be discussed in the next video. Thank you very much.